Okay, in class I said that we'd do one more of these mass defect nuclear binding energy problems. Okay, so I just made one up. They're very easy to make up. Just said, what is the mass defect nuclear binding energy in joules of carbon-14? Okay, and I give you the stuff that I always give you. I'll always give you these conversion factors and the mass of the particles. Okay, in both kilograms and AMUs. Okay, and sometimes I'll give you only an AMU. Sometimes I actually will only give you in kilograms, but you'll have the wherewithal to figure it out. Okay, first thing of noting, I didn't give you the mass of a carbon-14, so you should probably figure that out. A quick Google search of carbon-14, and you'll see that the actual mass is ... Get my marker going. Okay, I apologize for the software here. It is atrocious. I haven't figured out what to do yet. The Mac operating system update rendered my last software package for my tablet obsolete, and we're making do what we have. Okay, so I looked up carbon-14 and I found out that that is the actual mass of a carbon-14. Okay. Before we do that, let's take a step back and just talk about what we're talking about, right? We have mass defect, which was that phenomenon of the parts weighing more than the whole, okay, which is kind of a phenomenon. It's a freak of nature, I guess you could say. Okay, we have the actual parts being less than the whole, and it doesn't make sense whatsoever in the general scheme of things. Okay, it only makes sense in high grade modern physics. What I mean by that, I'm talking about the whole relativities and things like that, where we have a missing mass basically, and that's called the mass defect. We have a mass differential between the mass of the atom and the mass of the parts. And then we talked about in class that that missing mass was actually the m in E equals mc squared. Okay, when we're talking about holding an atom together or the nuclear binding energy. Okay, so we have to find out what the mass of the missing mass is, the mass of the missing mass, and throw that through equals mc squared. Okay, first step, know that carbon-14 can also be written as carbon-14 like that. Why is that important? Well, these numbers are important, right? We have 6. 6 is my number of protons, number of electrons. Subtract them, you get 8. Okay, and that's number of neutrons. It's important to know. And this is the mass of the carbon-14. Now we have to know the mass of the parts, which is going to be that column multiplied by that column. So let's start and actually do that. Okay, and you know what? I'm actually going to erase. Let's just do it like this. I'm learning from my mistakes that I did this problem about 15 minutes ago. And first of all, the first mistake was that you don't spend 15 minutes on a problem without actually knowing that you're recording. I did the whole problem and it was a total waste of time because it didn't record. But the second mistake that I'm learning from is that I always had issues on the margin. So I'm trying to start this a little bit more to the left. Okay, so I'm multiplying the two columns together. I have 1.00728 AMU. Show your units. 1.00866 AMU. 5.48 58 times 10 to the negative 4 AMU. And multiplying that out, you're going to get 6.04 368 AMU. I get 8.06928 AMU. Make that a little nicer. Using my E button for the times 10 to the negative 4, I get 0.00329129148 AMU. And the mass of the parts, I crunch these numbers and I get, you can already see it's a little over 14. I get 14.11625 AMU. Okay, and the mass of the whole thing was 14.00324. That's what I erased. All right. That's what I looked up online. So you can see that we had this discrepancy where the parts are heavier. First check. And first of all, this is third grade math we're doing here. This is rocket science. Okay, it's rocket science, and literally is rocket science in the quality of thought of what we're doing, but the actual steps involved aren't so bad. Okay, first check is that always, always, always make sure that your parts are heavier. They should be just a skewsh heavier than the actual atom, and it looks to be that's going to be right on, so that works. A lot of times this number will be off, and it's a simple mistake of having those counts wrong. Maybe you have the 668 or 866. Okay, maybe you did the subtraction wrong for the number of neutrons. Okay, so it's always nice to slow down and check. First question is, what is the mass defect? So that's where we do our subtraction. Remember, mass defect is the missing mass. And I'm subtracting, I'm going to get my missing mass of 0.11301. Okay, that's my mass defect. And I'm going to box it. I like boxing answers. You should really get into a habit. Okay, boxing numbers for your reader is really, really important. Just, maybe if I can look and see that you got this, maybe I'll not notice a mistake that you made with units or something like that. Okay, it's nice to just have the end result. It makes the reader, of course, who am I talking about? I'm talking about myself, the reader. It's just easier to check. So that's the mass defect. That's the missing mass, the mass that got converted into pure energy, the binding energy. So now we're going to run this missing mass through our equals mc squared, but before we do that, since they want it in joules, and a joule is a kilogram meter second squared over second squared, it doesn't have AMUs in the picture. We have to convert to kilograms. So I'm going to do that now. I'm going to take the 0.11301 AMU. Let me use this conversion factor right here. 1 kilogram on top, 6.02 times 10. Whoa. 10 to the 26. Okay, and that is in AMUs. Battle Royal, the units, AMUs are now gone. Kilograms are on top. Okay, we're going to have a kilogram mass of 1.8773 times 10 to the negative 28. First of all, that is a small number, times 10 to the negative 28. It should be. Okay, that's where the E button is really important. If you're not using the E button, sometimes this number would be positive, and that means it's like the mass of the Earth. Okay, it should be a very, very small number, negative to the 28. That means you have 27 zeros in front of the 1. 0.000000000018773. Okay, it's a small, small number. Now I'm in kilograms. I can finish this problem out. Okay, by putting my 1.8773 times 10 to the negative 28 kg times 3 times 10 to the 8. Okay, that's the C right there. And that is meters over second, and that's also squared. Okay, crunching numbers there. Remember, the E button is important. Crunching my numbers, I get 1.6895 times 10 to the negative 11. Okay, and that's kilograms. Of course, looking back there. Meters second over second squared, which is the same thing as saying 1.6895 times 10 to the negative 11 joules. Boxing my answer. Okay, note that typically when we do these problems, we're getting times 10 to the negative 11. Okay, I believe that's always the case. Times 10 to the negative 11, maybe times 10 to the negative 12. I don't think so. I think they're always to the negative 11, to be honest with you. So that's another check. First check is that when you're comparing these two numbers, this one should be heavier, right? The part should always weigh more than um, the whole, okay? And then this number should be small, okay? That means you screwed up if it's not small. And this one should also be small, about times 10 to the negative 11. So that's my two answers there, my mass defect and my nuclear binding energy in joules. This is the mass defect. I can see that in the second go around, I actually did this in about 3 minutes shorter, so it's good for us. All right, so there it be. Have fun with that.